We'll continue on the hydrolysis salt, part 3. What if the salt has both acidic and basic ion? Then how do we know if the solution is acidic or basic, or perhaps it's neutral? Well, you're going to have to look at its Ka and Kb values to determine whether this solution is more acidic or basic. So for example, HCO3- bicarbonate is amphoteric, meaning it has the ability to be an acid and has the ability to be a base. So if I were to have that particular sample after it has been ionized, it could go, say, in an acidic direction where hydrogen is donated to form hydronium ion. Ooh, there should be a 3 right here. And then it gives you the Ka value. If you know the Ka value, then say if this is acting as a base. If it acts as a base, then it's going to accept the hydrogen from the water, forming hydroxide and the H2CO3. And then you look at the Kb value. Notice that the Kb here is much greater than Ka, right? It's 10 to the negative 8 and negative 11. So negative 8 means that it is a bigger value. So therefore, we consider this as a basic solution because the Ka value is smaller. Okay, Ka value. That's how we can determine by comparing the Ka and the Kb value. So knowing that, we can do a learning check based on this. Determine the aqueous solution of the following salts are acidic, basic, or neutral. So we're going to go do all 4 of them, or all 3 of them with you. So let's do A. So if I were to put this in water, then I will have a K plus and a Br minus. Now, if that interacts with water, what will it form? That's my question. Or will it form at all? So for potassium, having this K, there's no hydrogen to donate. So obviously it's not going to be an acid. So will it be a base? Meaning, will it accept the hydrogen? Not quite, because the hydrogen is H plus. They're not going to want that. So there'll be no reaction. For Br minus, is this going to act as an acid? Well, no, because there's no hydrogen to donate. Will it act as a base? Yes, it can. It can take that H and then form into HBr. And then we form OH minus. But what is the likelihood of happening? Well, HBr in itself is a very strong acid. So this is a really strong acid. We know this by looking at that chart, not the one here. You look at the strong acid and base chart in your reference sheet. We know it's strong acid. So the chances going into the right direction is probably 0, okay? Really, really small, so small. So we can technically say that there is no reaction on here as well. So what does this mean? That the solution for this is going to be a neutral. So since there's no reaction on top or bottom. Let's go for B. So for B, you'll notice that it is Na2HPO4. If this were to ionize, then you would have sodium, and you would have 2 of the sodium and HPO4. 2 minus? 2 minus. Yep. So because this is, well, let's look at individually. So sodium plus water, will they react? Okay. Probably not, because as same reason as potassium, sodium is a positive and it doesn't have an H to donate, so it's definitely not an acid. Can't be a base either, because it can't accept an H. Having plus and adding another plus would be quite challenging, so this will be no reaction. So it's really determined by the HPO4 to negative, this guy right here. Well, you'll notice that this is a polyprotic acid, but it really doesn't matter, because if I have HPO4 2 minus and say it reacts with water, Okay, then say it's going to, actually it doesn't matter. Say it's going to take out an hydrogen so that, or sorry, donate a hydrogen so it becomes an acid, so it acts as an acid. Acts as an acid. So it will become PO4 3 minus plus H3O plus. So if it's an acid, you look at the dissociation constant for PO4. And this phosphoric acid is on the very below, and notice that it's on the very edge. It's probably the K3. It's going to be the Ka3 because it's in the very last stage where it's going to donate its last hydrogen. So the Ka value for this, or Ka3 value for this, is 4.2 times 10 to the negative 13. Well, what if this amphoteric guy is going to act as a base? Well, if it acts as a base, it's going to accept a hydrogen forming into H2PO4 minus, and then water here. Well, then what's the Kb value here? It doesn't give you a Kb value. You can find all you want, but it's not. But we can tell we actually have the K value, Ka2 value here to solve for Kb. So Kb will then equal to the Kw all over Ka2. You might wonder, why is it Ka2 not Ka3 or 1? Well, it is Ka2 because it's determined by what will it become, what acid will become. And the acid is at the second protonation. It's at where it has availability of 2 electrons or 2 protons. So it's already gotten rid of 1, and it's on the second one, and it's going to become this when this reaction goes. So that's why we use the Ka2. So this is 10 to the negative 14 all over 6.2 times 10 to the negative 8. It's really small, it's hard to tell. And so the Kb value for this one, if you solve this out, it's 1.6 times 10 to the negative 7. All right, so that's my Kb. So let's go ahead and compare the Ka, which is right here, and the Kb. Which one's a bigger value? So hopefully you are able to say it's this one right here, and that's because it is negative 7 is much bigger than negative 13, so Kb is bigger than Ka, so therefore basic solution. All right, so I want you to try the NH4F on your own and come back and check this video if you got it correct. I do have the base ionization for ammonia, not ammonium, but ammonia, its counterpart. And so use this as a hint in order to solve for that particular problem. And here is the key.